Hello. Now we're going to look at some lift example, which is basically very similar to what we just had in the last example of the Newton's second law video. So we've got a lift and its passengers have a total mass of 400 kilograms. So if you imagine a lift, and these are very basic, I don't know if anyone here is afraid of lifts, has some sort of fear. Very sorry if you do. And this lift is dangling on a cable here. Now, in real life, okay, there's a little bit more holding your lift up than just a little piece of string like this, but just go with it for these examples. There's a lift and everything inside it has a mass of 400 kilograms. Find the tension in the cable supporting the lift and there's 4 different scenarios, A, B, C and D. So first things first is what forces are acting on this lift. Well, there's the tension in the cable that's going to pull it up or hopefully stop you from clattering to earth, sorry. And also trying to pull you down is your weight, which is your mass times gravity. So there's 400 gravities there, 400 times 9.8, trying to pull you down there. So they're the forces acting on this lift. Now let's have a look at the different scenarios. So A asks us, find the tension in the cable when the lift is at rest. So if you are at rest, the first thing you need to notice, hopefully, is that that means that you are not accelerating. So your acceleration is 0. So when I then apply Newton's second law vertically to this, again, I should pick a positive direction. My acceleration is 0, so I'll just pick up as positive. Again, it doesn't matter which direction you pick as positive, you're going to get the same answer. Sum of all the forces equals the mass times the acceleration. Well, my force up, take away my force down, because I've chosen up to be positive, is equal to mass 400 times its acceleration 0. So that's just going to be 0 on the right hand side there. So your tension is equal to 400 gravities in newtons. Is that going to be 3,920? Is it something like that? Whatever that will be. So that's fairly straightforward when the lift is at rest because your acceleration is 0. Now, what they want you to notice here in part B is the lift is moving at a constant speed. Now, even if the lift is moving at a constant speed, that still means it's not accelerating. So even for part B, oh sugar, get a pen. For part B, then even though the lift is moving this time, it's actually not going to change anything about the force in the cable. The amount of force that has to be used in that cable doesn't change because your acceleration is still 0. So that's going to be the same, and your tension is going to be 400 G. There we go. So again, it's very important that you notice that when we're talking about acceleration, that's different to just something moving at a constant speed. Because if something's moving at a constant speed or at rest, then your acceleration is 0. So you're going to get the same answer from Newton's second law there. Okay, so fairly straightforward so far. If I just erase this big fat rubber, great. We'll now have a look at a scenario where we are accelerating. So part C says accelerating upwards with 0.8 meters per second squared. So you're going to have an acceleration upwards of 0.8 meters per second squared. So in this case, I would still pick up as my positive direction because I'd always try and take the direction of acceleration. And then if I apply Newton's second law vertically to this, I've picked up as positive, so the sum of all of my forces equals mass times acceleration. My forces up are tension pulling me up, and pulling me down is the weight in the negative direction. That equals the mass times the acceleration, 0.8. So again, I know what gravity is, so all I've got to do is all that's tension equals 400 times 0.8 is just 320. Add that 400 G on there. So my tension ends up being I get 4,240 newtons, which is more than the 400G that we had before. I think 400G, what do I say, 3,920, something like that. This is a higher force, obviously. If you've tried to move something and accelerate it upwards, if you're thinking of maybe holding a weight out with your arm, trying to lift it up, then doing that is a lot harder than just holding it still, just trying to hold it in the same place. That's because you need more of a force to accelerate it upwards than you do to just hold it still. There, so that kind of makes sense. D then asks us, what if the lift is accelerating downwards with, let's get a little bit of a smaller rubber, there we go. If your acceleration is downwards, finish lift off, there we go, 400 kilograms. Your acceleration is downwards, bump, bump, 0.6 meters per second. Squared downwards in this scenario. So a little bit smaller again. Yeah, that should be better. There we go. So if I just get rid of this quickly, then I'm going to swap my positive direction around as well. I'm going to say, okay, because I'm now accelerating downwards, then my positive direction is going to be down. And now then we still do the same thing, so we have a look at Newton's second law vertically, and we say, well, that just tells us that the sum of all of the forces equals the mass of the object times its acceleration. The only difference in this case is that downwards is now positive, so my 400G is a positive force, and my tension is upwards. The mass is 400 times 0.6. If I put my tension over, should equal 400 gravities. Take away 400 times 0.6 is 240. So T is equal to, in that case, 400 times 9.8 minus 240 is 3,680 newtons, so less of a force in this than part C. And again, if you think about it, if you're lowering something down, that's what's happening here, you're accelerating it downwards, then again it feels a bit lighter on your arm than if you have to pick it up. And that's because you need less of a force holding it up there in order to do that. Okay, so it's very important to think of a positive direction. Then the forces that you're going to get really are just going to be your tension in the lift cable going up and your weight of the lift and everything inside it going down. Newton's second law, they pick a positive direction, probably go with your direction of acceleration. The sum of all of your forces, everything positive, take away everything negative, equals the mass times the acceleration, and you should be done. Thank you.